Polynomial divisions. It's the basic division algorithm. It's the same for numbers as well, where you have ax times qx plus rx. The difference is these are polynomials instead of numbers, but we still have a divisor, a quotient, and a remainder. Same as normal division. A couple of notes though, when we're dealing with polynomials rather than numbers. The degree of the remainder needs to be less than the degree of the divisor. That makes sense, because if the degree was the other way around, you could keep dividing. And the quotient and the remainder are unique. Well, they have to be unique, because if they were the same, then you could factorize them. In other words, you could keep dividing. Very old question. Here's an example of one. They want us to find the quotient and the remainder when we do this particular division. Let's set it up. I think the things to keep in mind is, even if there's not a coefficient for a certain term, we add it in. So we can think of columns for each of the particular terms. The x cubed term has a column, the x term has a column, so we put that in there. And what you need to remember when you're dividing, you're actually dividing the terms, not the coefficients, and you only really are dividing the leading terms. Now for this one then, I'm simply saying, well, what's x to the power of 4 divided by x squared? I'm just looking at the leading terms, and that is of course x squared. Alright, now we'll multiply by the x squared and write my new polynomial down. Do a subtraction, bring down the terms I haven't used yet, and then we just do it again. So alright, x squared into minus 2x squared gives me minus 2, and I end up with a remainder of 3. So to answer their question, find the quotient, x squared minus 2, and the remainder 3. Okay, wow, even older. Divide this polynomial by the quadratic over there. X squared into 2x to the power of 4, 2x squared. Do myself a little subtraction, bring down the terms I haven't used. X squared into minus 4x cubed minus 4x. Multiply out, and we can keep going. So negative 2, and we have a remainder of negative 1. Now this question simply said divide it. So I suppose technically I've done it. I could have left my answer like that. And the reason I do, because this particular year, they then said, oh, hence go and write it. In the next question I'll go write it, and there it is. So we have it with the quotient times the divisor plus the remainder of negative 1. So back to the idea of graphing polynomials. When we do our polynomial division, we could rewrite it like this, where the fraction becomes quotient plus the remainder over the divisor, and that tells us a lot of information. Bottom of the fraction can't equal 0, that'll give us our vertical asymptotes. The quotient turns out to be the, well, horizontal or oblique, depending on what that turns out to be. I mean, theoretically, it could be a parabolic asymptote if that was a quadratic. Remember, all those asymptotes are doing is telling us what it's doing as we're out of the extremities. So if it does happen to be, say, y equals x squared, then we know our curve would get very close to being y equals x squared out at the extremities, so going off to infinity. And the top of the fraction, because of course we're allowed to cut horizontal and oblique asymptotes, unlike the vertical ones, and that will locate whether or not it does. So if it's possible for the remainder to equal 0, that'll be the x value where it cuts the horizontal or the oblique asymptote. Okay, well, let's do this one then. It's already been done for us. We've already got it in the form quotient plus the remainder over the divisor there. Vertical asymptotes I know will be at plus or minus 3. Bottom of the fraction can't equal 0. Pop those in. We know there's an oblique asymptote for this one. Y equals x. Let's put that in. Top of the fraction, yes, that can equal 0. At x equals 0. So we know it's going to cut that oblique asymptote there. And that's in fact what it ends up looking like. You know, we can get that now from just using the simple idea of, we know curves bend towards asymptotes. That'll do us.